To lecture 6 of mandate 1 in the course on topics in artificial general intelligence. In the last class, we looked at some models of what is meant by intelligence, right? And we were talking about how artificial intelligence is actually forced to address a lot of issues that were hitherto in the realm of philosophy, right? Or what is intelligence, what is consciousness, ethics, and all kinds of things. But even as we speak, there are great technological advancements, which do really amazing things that were considered part of intelligent behavior. For example, route finding, responding, reasoning, all kinds of things that machines can do already, right? Recognizing objects and so on. Yeah. So we need to have some kind of a good definition of what is meant by intelligence. And if you have to answer these questions like whether can we ever get to AGI, right? What is artificial general intelligence, right? So we need to have some kind of notion of what is meant by intelligence. So we saw two kinds of models for intelligence in the last class. One was about observable behavior. So this goes back to the traditional Turing test model of intelligence. That is, if something observes or is observably acting intelligent, then maybe it is intelligent, right? And so we saw how the formulation of this is in the form of a Turing test, where there's a conversation between a person and an agent and so on. Then we saw yet another model of intelligence where we looked at intelligence as simulation, right? That is, if we can simulate something that is intelligent, right? That's something that we term to be intelligent. Okay? For example, the human brain, right? And so if we are able to simulate the working of a brain, then maybe we can replicate whatever the brain does in a machine, right? And so that is the idea behind intelligence as simulation. So let us move further in this lecture today, and we look at some more models of intelligence and how they have shaped the way AI has developed over the years. Okay. So let me start by sharing the screen. It is visible now. And you can see the image of a cat over there. So we'll come to that in a moment, what this is about. So the third model that we are going to look today is the idea of intelligence as an ability for conceptual modeling, right? What do we mean by what do we mean by this, right? So this is what we are going to look at here. So. Okay, so what do we mean by conceptual modeling, and why is it a measure of intelligence, or why is it an indicator of intelligence? So conceptual model is a model that you build about how the world functions, and which we can use to intervene or to reason and to strategize and so on, right? And so most of our considered activities and even sometimes subconscious activities are driven by some kind of a conceptual model or a mental model, sometimes it's called. And, so how is mental model different from, say, that of simulation that we were talking about in the previous case? So the idea of a simulation is that you're trying to replicate exactly what is happening in something that you're trying to simulate, right? So if we are trying to simulate the brain, we are trying to understand how exactly the brain functions and replicate all those structures and processes in the computers. Okay? But with conceptual model, a conceptual model is an abstraction, right? Where it need not exactly replicate everything that happens over there, but maintains the essence of what is happening over there in a very compact abstract model. Okay. So again, the idea of conceptual modeling also relates to the strong AI claim made by Neville Simon, who basically said that a physical system symbolic manipulation system. So earlier this was called symbol manipulation. So a physical symbol system has all the necessary and sufficient means for general intelligent action. So that was a claim made by Newell and Simon. So a conceptual model basically, like I said, consists of abstractions. So we have mental or symbolic representations of all the entities of interest in our mind and the relationships between them, the constraints, the rules of manipulation, and so on, right? And typically the tools that we use for conceptual modeling and reasoning is basically logic and entailments and proofs and grammar and language, and so, right? And so this is the kind of so why does conceptual modeling indicate intelligence? So there is this parable called the parable of the hungry cat. So right, which kind of tells us about how conceptual modeling works and so on. So the idea here is that there's a man who has a pet cat in his house, and every day when he comes home, the cat is there and it's very hungry, right? So the cat immediately comes running to him and keeps jumping on his legs, asking for food, asking for something, right? And it doesn't let him even take one step. It keeps coming between his legs and keeps on meowing and so on, asking for food. And with great difficulty, he goes to the fridge and tries to take out some milk, but it keeps on jumping. And most of the times he invariably drops the milk and it just licks the milk from the floor and goes, right? And it's satisfying. So basically the man is perplexed. No, why isn't the cat learning that that you're that you are going to feed it, that he's going to feed it, and it just has to wait patiently for some time. Okay? So one of the explanations for this is that the cat has actually learned from associations, right? So what has the cat learned? The cat has learned that if it somehow comes between his legs and keeps on demanding, okay, somehow milk will fall from above, okay, and you get milk, right? So it is actually getting rewarded for its behavior, right? It is actually getting rewarded that that by jumping and demanding incessantly is actually resulting in it getting what it wants, right? It gets its food. So what is the problem here? The problem here is that the cat seems to be unable to build a conceptual model of the person's intentions, right? So the person, does it know that the person intends to feed it? Okay, it doesn't have to actually jump. Okay, so the person intends to feed that, and the person has a particular way of feeding it. So he goes to the place where it usually sits and pours the milk and so on. So the best strategy to help this happen is to go and sit silently, right? And so it's not able to build a conceptual model comprising of latent elements like intents, plan, right, goals, and so on, right? And it is actually building some kind of a much more rudimentary conceptual model where it is computing associations, saying that, okay, if I do this, I'll get this. If I do this, I'll get this, and so, right? And so that's the idea of intelligence as conceptual modeling. That is for the same intended output, okay, and the same kind of associations, we can actually build different kinds of conceptual models at different levels by bringing in a lot more latent entities like intents of others, and the plan of others, the beliefs of others, and so on, right? And beliefs of myself, and so on. So all of these kind of help to build a good conceptual. Okay. And of course, the idea of conceptual modeling, was very popular in the first wave of AI, and there were lots of advances made in what are called description logics, which are basically formal mechanisms for describing a universe of discourse. And reasoning about that, and reasoning about conceptual relationships and so on. But pretty soon there were several complications that came about, even though it promised a lot of things, there do exist some very impressive systems based on formal logic even today. And today, for example, we have a lot of formal reasoners and program verifiers and all kinds of things which are based in formal logics. And much of the groundwork for this was made during the first wave of AI. But now we know that there are several limitations to the kind of formal logic that we have built. For example, in most real-world conceptual modeling, it is hard to represent crisp modalities for truth, right? So we can't just speak in terms of true and false, right? And so crisp logic, or what is called first order predicate logic, second order, or any kind of higher order predicate logic, are basically crisp logics in the sense that an assertion can can either be true or false, okay, and nothing in between, right? So this is also called the law of the excluded middle, right? Law of excluded, right? Which basically says that you can't make a statement that is both true and false, or neither true nor false, or half true and half false, or something like that, right? It's either true or it's either false. And so on. So, but in real world, what happens is we don't know the truth of a lot of assertions because of a lot of complications. One of the biggest complications we get is that we live in what are called open worlds, right? So, what is an open world? In an open world, we don't know a whole lot of facts that are there, and more importantly, we don't know what we don't know, right? That is, we are not only ignorant, but we are ignorant of our ignorance, even, right? And so for that reason, many times we cannot make an assertion with absolute certainty of its truth or falsity, and so on, right? So we need different modalities of truth, right? So there are several modal logics which have been developed for this reason. We'll cover some of them in the next mandate, which tries to qualify truth in different ways. But qualification of truth comes with its own complications, right? And of course, the third complicating factor is the unknown itself. That is, something could be true or something could be false. And something it could well be unknown. An assertion could be an open question or open problem, right? And we may not know how to factor this. Okay, so this is the idea of the closed world reasoning complications. So closed world reasoning is also called ignorance is falsity, right? So what is meant by ignorance is falsity? It means that whatever we don't know to be true, we assume to be false, right? That is only that we know to be true are assumed to be true, right? And so if I don't know whether, for example, eating corn causes corona, whatever, right? And then I assume it to be false, right? And I don't know whether something is true or false. And I basically build my models on only the assertions or axioms which I know to be true. Then there are epistemological complications. So, for example, I talked about beliefs, right? And so many times, we can build completely consistent logical frameworks based on completely different sets of beliefs, which can be abused from the same set of observations, right? That is, two people observing the same thing, same set of observations can build completely different but consistent belief systems out of that, and build a complete logical framework out of this, right? And so there's no one, and these are what we call epistemological complications, right? And there are also complications regarding knowledge, right? So whether I know something and whether I know that I know something, right? And whether I know that you know that I know something, and so on. Right? And, so there are issues like global knowledge, common knowledge, and so on. We'll again cover some of these in the next mandate. So what is meant by common knowledge, and why is it important, or why the lack of common knowledge can really make things really more complicated. Okay. Then there are issues like what are called frame problems. Frame problems basically means is that a lot of reasoning that we do as humans rely on what we colloquially call as common sense, right? Common sense tells me that this doesn't happen. Common sense tells me that this doesn't happen, right? And but there's no specific modeling of common sense. Now we need to specifically model common sense, knowledge in any system, right? And so for that you need a huge amount of explicit knowledge that should already be there, right? And, so I've given an example in the next slide here. So so let us say I have an assertion which says let's say if I write something like on of t, right? So something like this. It means that the light is on at time t, right? And let us say the assertion here, open of t, means that the door is open at time t. Okay. Now suppose I know that these two are true, right? I know that not on of 0. What does this mean? This means that the light is not on at time 0 and not open of 0, right? That means the door is not open at time 0. Okay. Now, and then I'm given an observation which says that open 1, okay, which means that the door is open at time 1. Okay. And now, if we ask the system to answer whether the light is on at time 1, right? Now, there's no entailment to it. There's nothing to say that to conclude whether the light should be on at time 1. Okay. So, according to common sense, okay, we may say that okay, the door opening or closing has nothing to do with the light. So maybe the light is still not on, because it was. But of course, what if it is a refrigerator door, right? I mean, if the door is open or closed, the light comes on and off, right? And so they could actually be connected, right? And but there's no entailment, right? Unless we specifically mention how these two are connected, we cannot entail something, okay? But in reality, what we do is we have some default behavior of things. So by default, we assume that okay, there's nothing that is connecting, and then we say that no, it's not on. So so there have been some criticisms about intelligence's conceptual modeling or symbolic representation as well. So we'll look at one specific criticism of this is what is called as the physical grounding hypothesis, right? And which was this guy called Rodney Brooks, who is a very well-known name in robotics, first proposed this in a paper called "Elephants Don't Play Chess." So, right, and so we'll see what it means and why this comes as a criticism of symbolic reasoning as a measure of intelligence or a marker of intelligence. Okay, so that was quickly about a quick overview of intelligence as conceptual modeling. We have one complete mandate on conceptual modeling and knowledge representation coming up. So we'll do much more deep diving into conceptual modeling. What do we mean by conceptual modeling, and why is it that there is a lot of evidence to suggest that human beings have an innate ability for building conceptual models. Not just human beings, a lot of animals have different kinds of conceptual modeling abilities. Dogs have some kinds of conceptual modeling abilities, and cats have some other kinds of abilities, and so on. So I gave this example of how the cat was finding it difficult to understand intentions, right? But dogs are very good at that, right? I mean, dogs are known to understand our intentions much better and which is the reason they follow orders much more than what say cats can do. Okay? So how we can how do we come to represent these kinds of latent concepts, okay, and incorporate them as part of our model? Right? So we'll look into some of these in more detail in the next one. Okay, so the next model that we are going to see is what is called intelligence as embodied cognition, right? And so this kind of became very famous or very popular among AI through through robotics, basically, right? And so if you have seen robots from the 70s or 80s, I don't know how many of the viewers here would actually remember or know that there existed, there used to be a TV series, Japanese TV series called Giant Robot in the 1980s, okay? And it was about a giant robot which came to save the world and so on, which is what everything did in those times. And but what is characteristic of that was if you can go and search for giant robot on YouTube or something, you'll see how the robots at the time were, right? And it had very stiff movements, right? The arms moved like this and very, very stiff movements like this, very stiff walking and so on. Okay, but then we saw in an earlier lecture today, some robots by Boston Dynamics, right? And which were actually dancing, which were so versatile in the way that that they were able to move about, okay, which was unthinkable in the 80s. Okay. So what brought about this change, right? The reason robotics became so versatile in the recent past is that the underlying architecture of stimulus and response was greatly altered by an architecture, what is called as the subsumption architecture, right? I'm mentioning here, okay, which was proposed by Rodney Brooks in this paper called "Elephants Don't Play Chess," right? And so what is this architecture, right? So in order to understand this, we look at how the architecture of sensing and perception and action existed earlier, right? So earlier, the control loop for robots was something like this, right? There was a sensing module which sensed the state of the system outside of the environment and the stimulus and so on. And based on that, there was a perception module which recognized objects, which recognized relationships between objects and so on. And from the perception module, there was an interpretation module. So it interpreted what was happening and what it needs to do and how it needs to respond and so on. And then there is an action module, okay, which actually performed the action. Okay. So this was the entire control loop in the previous architectures. But this control loop can turn out to be extremely expensive, right? Because even performing perception, interpretation, and converting them to action in real time can quickly become extremely expensive, right? And so which is what made the robotic reflexes, so to speak, very rigid, right? And but what does the subsumption architecture do? So the subsumption architecture basically, has several layers in which the control loop operates, right? So there is a lower layer which has very simple logic about avoiding objects and so on, right? And so there's a very simple logic that that a lower layer does, and all it can do is how to avoid colliding into something. Then there's a next higher level logic which talks about exploring, wandering, or something like that. Okay? So which with a slightly more sophistication, right? And even more higher level which can explore the world and exploit some mechanism over there, right? And so when a stimulus comes in, that is when there's a sense and information that comes in, it is fed to all the modules at once, right? And the higher level modules or the higher level layers, because of their higher sophistication, are generally slower to compute what is the action than lower level layers, right? The lower level layers compute very quickly, while the higher level layers compute, in a slower fashion. So, okay, and each of these actions come out like this. Okay, and at any time, if there's a response from a higher level layer for a particular kind of response for some actuator, let us say, and if there is a lower level actuator response for the same actuator coming, then the higher level response subsumes or overrides the lower layer response, right? And so what does it mean? If we can compute sophisticated responses in real time, we'll use that, okay, to respond. If we can't do that, we will respond from a lower level, a reflex layer. Okay. So this is the idea of subsumption architecture, and there's a lot of evidence to also note that even human cognition, is organized as in a subsumption architecture, right? And so even in human cognition, what happens is that let's say we are speaking to someone, okay, and let's say they say something that we find offensive, let's say, right? And so if we notice carefully, we react at different levels, right? So there could be a visceral or reflex action that we may get offended, we may lash back at them or something like that, right? And but at the same time, we are also processing the same thing at several different layers, right? We are trying to understand why are they saying like this, or maybe what is their belief, what do they understand, and so on. And typically, compute some higher level responses as well. And if we are able to compute this, then these responses mask our reflex actions, right? By reflex, we may want to snap back angrily, but if you are able to compute a higher level, more nuanced judgment, this judgment would actually mask the lower level responses. Right? So even human cognition basically operates in a layered fashion like this, right? Where higher level layers compute a more sophisticated response, and their proposed actions subsume or override the lower level actions, right? And not just actions, even recognition of something, okay, also happens at different semantic layers, right? For example, if we are given an apple, okay, if we show an apple to a child, okay, you don't have to actually show 10,000 training samples, like we do for a neural network, in order for the child to recognize an apple, right? And so a child can recognize an apple by just seeing one or two examples of it, right? And so how do we do that? How is that our training data is much lesser? How can we make do with much lesser training data? So, one of the reasons for this is that we don't just recognize physical features of the apple. Okay, I'm talking about superficial features like, say, the color, shape, and so on. While of course deep neural networks today can recognize a lot of things, so it can recognize not just color, shape, but also the object and the relationship with that, and so on. Okay, but what we can also do is that we take it to a much more deeper extent. That is, we recognize this as a fruit. We recognize it as a form of food, something that we can eat, something that brings us pleasure. Okay, something which can quench hunger, all kinds of things. We kind of recognize a whole lot of attributes to this object the moment we are given an object, which helps us recognize objects with much lesser number of training samples than say what we can do with artificial neural networks currently. So this is a quick idea of intelligence as embodied cognition. And what is the, why is the paper called Elephants Don't Play Chess, and so on, right? And so the idea here is that, so this is, until that time, intelligence, one of the markers for intelligence was something like whether a computer can play chess or can play Go and so on, right? And these are the kinds of problems that were being addressed in the field of artificial intelligence. But what Brooks is arguing is that, see, an elephant is intelligent, right? This is like the example I gave about a fish in the last class, right? And so elephants do a lot of intelligent things, okay? But it doesn't necessarily have to play chess for it to be considered intelligent. It doesn't have to really do some kind of abstract symbolic reasoning, right? In fact, we don't even need full-fledged abstract symbolic models, detailed symbolic models. So according to this paper, the world is its own best model. Okay, it is always up to date, and it always has every detail to be known. Okay, what we need to do is to sense it appropriately and often enough, right? And so the idea here is that intelligent behavior comes from sensing the outside world, often enough, interfacing with the outside world, and responding to it adequately. So that kind of builds different kinds of responses. So there's also sometimes what is called as a holistic model of intelligence. Here, perception, interpretation, knowledge, response, everything comes in one loop, right? So if we look at this figure again, so earlier sensing and perception and interpretation were all different modules. But here, if you see, each layer contains all of these activities, okay? Sensing, perception, interpretation, action, all of these, right? And so the entire set of control loop activities that made up a sensory response is considered in a holistic fashion. It's not considered in a piecemeal fashion in this model, right? And so this is the idea of intelligence as embodied cognition. And so what are the implications of this, or what are the philosophical implications of embodied cognition, right? So, and there's also what I mentioned, this is also what is called as the physical grounding hypothesis, right? And so philosophically, what this is saying is that a physical manifestation of an entity is necessary for intelligence to emerge, right? That is, a mind requires a body for the mind to be intelligent, or for an intelligent mind to emerge, right? And well, the symbol manipulation hypothesis basically says that it basically says that you can actually perform intelligent abstract computations without the need for a body, right? I mean, you can have a mind hypothetically stored on a computer, right? Which is not associated with any being or living being or body and so on, right? While the physical grounding hypothesis says that no, a living being or living body is necessary for intelligent mind to emerge. These two can also be seen. There's a similar debate in the field of linguistics. There's a lot of debate among linguists about whether language affects thought. Right? And so, does the language we speak, affect the way we think and so on, right? And so there's a well-known hypothesis called the Sapir-Whorf hypothesis. Okay, that talks about the mold hypothesis of language and mind, and so, right? And so the mold hypothesis of thought and language is something like this: that thought requires language for it to be recognized as thought, right? So it is something like, suppose you have a lump of clay, right? Now you have a thought about molding the clay into a bowl like this, or a nice idol, or some kind of statue or something like that, right? And so the idea in your head, okay, require the mold, the clay, in order to manifest itself, right? Otherwise you could not have conveyed what you're thinking, right? And so that's the idea of the mold hypothesis, that that language is necessary for thought to be conveyed, or right, and without language there's no thought. While the cloak hypothesis, which is more similar to the symbol manipulation hypothesis, basically says that a language is a cloak around thought, right? That is, language is a wrapper which wraps thought, and we kind of gift wrap a thought in our language and present it, right? And basically, when we consume the thought, we actually throw away the gift wrap, right, and then consume what is inside. So again, the evidence for this is that the fact that thought exists without language is that sometimes we find ourselves in a state where we don't have the right words to express what we are thinking, right? We may be thinking something, but we don't have the right words to express. Okay. So what does it say? It says that we are actually thinking without a language, right? Because we don't have the language to express what we are thinking, right? And so that's the kind of evidence that that the cloak hypothesis talks about. That thought does exist without language, and a language kind of wraps around thought. And to really understand thought, you need to remove linguistic constructs, right? You need to remove linguistic words and then look at the thought behind it. So these are two philosophical schools between language and thought, and similarly here between mind and body, right? When it comes to intelligence, which are very interesting, and which have both evolved into their own spaces. So we have a very rich space of symbol manipulation software and symbol manipulation results. We have semantic web, for example, and we have knowledge graphs, we have natural language processing, so many kinds of things which come directly, only uses symbolic processing. While we have robotics and autonomous vehicles and agents and so on, which use a physical grounding hypothesis in order to manifest their kind of models. So these are again two completely parallel kinds of schools of thought, both of which are interesting for us to understand what is meant by gentle cognition. Wonderful. So let us stop at this note, and in the next lecture we'll look at one more model of cognition, basically, or one more model of intelligence, basically the concept of free will, right? Intelligence and the notion of free will. Okay, is free will necessary for something to be called intelligent, right? And which brings us to the concept of agency and autonomy and so on. So that we'll look at in the next class. Thank you, and see you in the next lecture.